Earlier, we were talking about generalized method of moments, the theories of generalized method of moments. Today, we're going to talk about some applications in MATLAB in R of the problems in generalized method of moments, chapter 10. The first problem, method of moments estimation. The exercise is based on data in table 10.1. The methods of moment estimator of theta for the just identified model. Okay, let's have a look into the data. We are in page 33, table 10.1. We can just jump into table 10.1, or yeah, let's just scroll up. The first table we're talking about. Yeah, so in the table we have yt square, yt cube, y2 to the power 4. Then first uncentered moments, and then log yt and 1 by yt, all in columns, and they are estimated. Generalized method of moments are being estimated, or empirical moments are being estimated. Okay, so this is the empirical moment, is based on the solution of empirical moment equals mean sample population moment is equal to 0, where the moment function is the moment at time t. Now we're talking about normal distribution, where 1 by root over 2 by sigma square, the probability distribution function is 1 by root over 2 by sigma square exponential of minus half yt minus mu divided by sigma whole square. The normal distribution has moments of mu. Variance is sigma square plus mu naught square, sigma naught square plus mu naught square, and yt minus sigma naught to the power 4 equals 3 sigma naught to the power 4. This is the third moment, and it is asking us to do estimate moment conditions. First are uncentered moments, which is yt minus mu, then y square minus sigma square, the variance minus mu square, obviously because there is an additional mu here, and the uncentered moment conditions. And in centered moment conditions we have yt minus mu, then which is yt minus theta 1, then yt minus mu to the power 4 minus 3 sigma to the power 4. This is the second moment here. In terms of student's t distribution, we know instead of sigma square we just put tau divided by tau minus 2. Now here the second moment is, well, 3 sigma naught 3 tau square divided by tau minus 2 multiplied to tau minus 4. This is the second uncentered moment. So moment conditions are obviously this is the regular moment condition, and uncentered moment and centered moment. In terms of gamma distribution, we have this equation representing gamma, where beta to the power alpha divided by tau alpha exponential of minus beta yt multiplied to yt to the power alpha minus 1 has the moments where alpha minus divided by beta naught, then as you know alpha square divided by beta square, or alpha naught multiplied to alpha naught plus 1 divided by beta naught square, and 1 by yt is equal to beta naught alpha naught minus 1. And we know that we do not take the second moment, we take the only first and the third moment, because this is so that we have exactly identified case, because this will be otherwise we have only 2 parameters but 3 equations, or an over identified situation here. We need to avoid that, and hence only the exactly identified is specified. So for specification we take the first and the third moment condition, 1 by alpha beta by alpha minus 1, and uncentered moment condition and centered moment condition, where alpha plus 1 divided by beta square. Compare the two sets of points Point estimates for alpha and beta. Briefly discuss the potential problems associated with estimates based on moment conditions in part 2. Then another distribution we did not talk about in our theory is the Pareto distribution, where alpha y minima y minimum divided by yt to the power alpha plus 1 is the distribution where the first moment is alpha naught to the power y minimum divided by alpha naught minus 1. Variance is alpha naught minimum of y squared divided by alpha naught minus 1 squared into alpha naught minus 2. And choosing the minimum of y to be 2, estimate theta equals alpha using the moment condition where yt minus alpha naught y minimum divided by alpha naught minus 1. Then estimate alpha using the moment condition, centered, uncentered, and then centered moment, which is y squared divided by alpha naught y minimum divided by alpha naught minus 1 squared divided and alpha naught minus 2. Simply yt minus this and this. That's all. So this is our first problem. So we have quite a bit of problems to solve. Have a look into GMM MOM. So we are already in GMM MOM, and for this one, okay, let's see if there are any. No, there is no local function. So first we need to generate random variable. How do you clean the screen in R? Is all equals true, is all true, list equals is all true, rm list equals is all true, graphics is off. Then we know in MATLAB simulation is initiated with random stream dot set global stream in bracket random stream mt1137ar 12345 seed, then 12, and is easier in R, which is set 12345 type kind Mersana twister. Then helper function, that is added is sourced this. Now in our problem we have how many data? We have t equals 10, right? 10 because basically we are to estimate 10 parameters here. Otherwise there is nowhere given t equals 10. We are the number of parameters that we are going to estimate in total. Number of moment conditions we are going to estimate in total is 10. So t equals 10. Generate data and compute SAM. Generate data and compute SAM, right? So what is SAM? Solution of moment. Generate data and compute SAM. Okay, we'll see about that. First we have to generate data. First we have to simulate the data. So yt is 5 plus we're randomly selecting 5 because I don't think there is anything that is hinting us get 5. Okay, or otherwise we can go to based on to. Okay, so empirical moments t equals 10, that is given in the table, and 5 is just an assumption here. It shows the computation of the first form uncentered moments, first two centered moments, the mean of log yt and yt. Okay. So 5 plus 2 into random number t rows 1 column. That's how data is being generated. We're taking the rounded number. So 2 into random number t rows 1 column, or r norm t multiplied to 2 plus 5 rounded. Then m1 is mean of yt. M1 is mean of yt, then mt is equal to yt squared, yt cube, yt to the power 4, yt square. See, there is an element by element multiplication. Yt cube, yt to the power 4, then yt minus m1 squared log of yt 1 by yt. Okay, then m is equal to mean of mt. Taking the mean of all of these, we form m, which is the empirical moment, mean of mt, or column means mt is the mean function. So let's just see both mt and its mean, both. So we row bind, they are coming in columns. The first one is, it forms a column. So row bind, first show me mt's, then m's. Compute various moments used for method of moment estimation. m2 mean y square, c2 mean yt minus m1 squared, and c4, these are centered moments. We're talking about centered moments here, or c4 m4 4m3 m3 into m1 plus 6m2 m1 square. So this whole thing, m to the power 4 and minus 4m3 plus 6m2 is coming from. So here what we are doing is that first moment is mu square, obviously yt mean squared. Then centered moment is yt minus m1 squared. Then c4 on the other hand is yt minus mu to the power 4 minus 3 sigma to the power 4. So we break the whole thing, break the whole equation. Then we replace anything that has yt, then yt square with mu and sigma square, or the or the generalized moment conditions. And we have this equation that we represent in R2 in the same manner. Then h1 is mean y by y divided by 1 divided by yt, which is also something we're estimating, because this is coming from the table, which was, I think, number 4. Yeah, 5 page. See, log of yt and then 1 divided by yt. So these are the equations. So normal distribution of mu sigma square is M1 and C2. So concatenate and display starts with an N, M1 and then C2. Normal distribution of M1 and square root of C to the power 4 by 3. Square root of C to the power 4 by 3, right? C to the power 4 square root of square root of C4 divided by 3. And where am I getting this from? Square root of C4 divided by 3, basically from here, square root of C4 divided by 3. Okay, so if you take 3 on the left hand side, then you can take a root over all, and you have square root of C4 divided by 3. The questions asked me to look into different point estimates. Okay, so 2 point estimates. First is for centered moment, and then for uncentered moment, 2 different sigma square, right? Obviously 2 different sigma square. You see, this is 1 sigma square, which is giving you, which is simply C2, and our C2 here is 20 minus mu squared. Then C4, we can't use sigma to the power 4, rather we need to take square root. This is another C2 for the uncentered moment condition. That's all, very simple. And then t distribution, mu and nu, or sorry, I was telling it tau is nu, 2C2 divided by C2 minus 1, right? Which is coming from here, 2C2 divided by C2 minus 1. This was, on the other hand, from student's t distribution, 2C2 divided by C2 minus 1. That is nu. Nu is 2C2 divided, nu itself is 2C2 divided by C2 minus 1. Or we can go back to our main theory here, and if we were to look into page 1, 2, 3, we see here nu is 2C2 divided by C2 minus 1. C2 itself is the moment condition. So 2C2 divided by C2 minus 1. Very simple. So that is coming from state distribution nu. We estimate nu's value. Then t distribution mu and t distribution nu based on solving a quadratic equation in nu. Now first root and second root, after we solve a quadratic equation for nu, we get this, right? And in this problem, 3 nu square divided by nu minus 2, nu minus 4. So this is the whole equation that we need to solve to get these points, right? The first root and the second root. So basically one will be plus, one will be minus, but so we'll get a plus minus result. But for that we need to put nu's value here and solve we need to solve the entire equation for nu, taking this one equals 0, and that will give us first root and the second root quadratic equation. And then gamma distribution. Then we look into gamma distribution, and our gamma distribution was, these are our gamma distributions. We see that with gamma distribution we have alpha hat and beta hat that we estimated. See, this is alpha and this is beta hat. Yt yt minus 1 by yt, alpha hat divided by 1 by yt. So gamma distribution m1 divided by m1 minus h1, m1 divided by m1 minus h1. See, m1 divided by m1 minus h1. Now h1 is 1 by yt. Alpha is h1. Have we mentioned h1 anywhere before? Mean of 1 by yt. That's all. So very simple. m1 divided by m1 minus h1, and beta is alpha hat divided by h1, right? So m1 minus h1 divided by h1, one more time. So m1 minus h1 divided by m1, I'm sorry, not h1, m1. So m1 minus h1, m1, this is beta. Then for that was for centered, for uncentered moment conditions, m1 squared divided by m2 minus m1 squared, or we can say, yeah, m1 divided by m2 minus m1 squared, m1 squared divided by m2 minus m1 squared, or m1 divided by m2 minus m1 squared. This is a gamma distribution of alpha and beta, and y mean is mean of yt. Pareto distribution is m1 minus y mean. So alpha, this is just from the Pareto distribution, because in Pareto distribution we had, okay, I think this one is not responding. Yeah, the Pareto distribution is alpha y mean, minimum of y divided by yt plus alpha 1, or alpha divided by alpha minus 1. So m1 divided by m1 minus y to the y mean, m1 divided by m1 minus y mean, or minimum of y, m1 divided by minus m1 divided by m1 minus y mean, m1 divided by the alpha is m1 minus y mean. Okay, so m1 minus y mean, this will yt alpha plus 1, so numerator and denominator will change. So m1 minus y mean, so m1 divided by m1 minus y mean. Okay, just remember this if we ever need to use that. So to find the roots of alpha, we need to find a we need to solve a cubic equation, minus 4 minus 5. So this is the cubic equation, and with other two, the first root is real, but the other two roots are the complex conjugates indeed. So alpha roots, Pareto distribution, alpha roots for Pareto distribution, moment condition. So we need to do some mathematics here for Pareto distribution. Just the roots of alpha. So we can use the roots function, polynomial roots function. On the other hand, in R, what we do is that first we create the column with the numbers of interest, c minus 4 minus 5 y square divided by m2 minus 2. Then the roots function, instead of the roots function, in R we have polyroot. The function is polyroot. So roots in MATLAB, polyroot in R, both of these gives us roots of the variables, and that's all. Alpha roots, and the first root we have is alpha roots. That is pretty much it. So GMM mom is done. Then comes the second problem. The second problem is GMM gamma, a gamma distribution. Now here also we'll base the data in table 10.1, but here we need to focus in a specific problem in gamma distribution. The specific problem in gamma distribution we have discussed earlier, I guess. Yeah. Allow me just 1 minute. Let me find out what is the problem that we discussed before. Estimating a gamma distribution. So high probability that we are talking about this problem, gamma distribution, where m alpha is, this is the uncentered moments and the centered moment, and we have the centered moment conditions. Uncentered and centered moment conditions. Just I'll keep this open. Well, I'm gonna go through the problem. Theta hat is minimum qt theta. We have to optimize this to find the minimum of qt theta, and we'll do this. I think we have done this before. Okay, this is consistent with our discussion in estimation in the theory. First of all, we need to remember that we expect that population moment, that our moment condition or the empirical moment should equal sample or mean of the population moment, which equals 0. Now that condition will not satisfy if we have an over identified case, which means we have more equations than parameters, number of parameters. However, in case of an exactly identified system, we estimate our model by minimizing the parameters, because the minimum values of the parameters let our empirical moment to be closest to 0, and that is something we have to keep in mind. Keeping that in mind, we move forward with this equation. We are minimizing in our exactly identified system so that our parameters, the empirical moment condition, reaches close to 0. We have qt theta, as we have already studied before, because this is the function, this is the moment function that we need to be minimizing, right? So this is the moment function, and mt theta, as we know, empirical moment. Wt theta, on the other hand, is simple. This is just to be used in cases for decomposition. This matrix is, this is the matrix Wt theta, Wt transpose, or yeah, and this is the decomposition here, weight matrix. Okay, this is the weight matrix. Now, which is also a squared matrix, a squared variance covariance matrix. So Wt is a n by n positive definite weighting matrix that determines how each moment is weighted in estimated. positive definite. By positive definite we mean the diagonal elements multiplied are greater than or equal the non-diagonal elements multiplied, and it is symmetric when the non-diagonal elements equal to each other. The first two uncentered moments of the gamma distribution with beta naught equals 1, EYT equals alpha naught, so y squared is equal to alpha plus 1. That is again the same thing here we were discussing, alpha plus 1. And this is the first two uncentered moment condition. Then we use starting value as theta naught and compute all of this with our algorithm numerically. This is the gradient, this is the Hessian, fine. Using the result, we use Newton-Raphson to update and compare this with the updated theta 1. Iterate until convergence and find the GMM parameter estimate of alpha and standard error. This we have all done before. We want to use these with not only alpha plus 1 but also 1 by alpha minus 1. And then we want to use these again for 1 by yt, where beta divided by alpha, the gamma condition, the third condition, beta divided by alpha minus 1. So estimating a gamma distribution, let us see how it goes, which is gamma. Gamma, and we have here gamma. Okay, so compute GMM estimates of the parameters of a gamma distribution. So first again, all true is all true, least equals is all true, RM, remove, then graphics of, then set seed 1 to 3 kind Marciana twister, and then we have to for gradient and Hessian we install numeric derivative, that package, and we also load the function emtsu TLR. Then we look for if there is any local functions. There are. So in case of first two moment conditions, we create a function called a GMM create with alpha. Inputs are alpha and y. Well, GMM create 2. The functions will take input alpha and y. M1 is 1 minus the first parameter. Then the first population moment, the second moment is y square minus alpha into alpha plus 1, simple. Then we do column bind, we want them in column. Now weight matrix is MM, as we know. Weight matrix is simply MM transpose, as we have seen. And yeah, weight matrix is simply mean of mean of M transpose, decomposition. So M transpose mean weight matrix, and Q is half mean M inverse W. This is the equation, the Q equation, half M inverse of omega and then M. So transpose of M multiplied to M divided by length of Y, then 0.5 column means of M inverse of W, then column means of M. Okay, so you have this equation because we will have to optimize this equation Q, and we use column means M inverse of W column, and then column bind. Instead of taking a transpose of the whole thing. This can be represented with column bind column. So this has been used before, we have to remember that. So whenever we call GMM create, it will return Q. Then a 3-moment condition, alpha y, when we have 1 minus alpha y square alpha 1 by y minus 1 minus alpha 1. This is the 3rd moment condition, 1 by y minus 1 divided by alpha minus 1. We are familiar with this. So now M will have 3 columns and the equation will return the same thing. And then we have objective function, 2-moment, 3-moment, 2-parameter gamma function. Now let's see what is a 2-parameter gamma function. Alpha. Okay, we are not only basing our estimation on alpha, this time we want to estimate alpha and beta both, right? And in that case, because in our problem we want to estimate not only 1 by alpha minus 1, we want to estimate beta too. So alpha by beta, alpha naught plus 1 by beta squared. This is the most commonly used where we estimate alpha and beta. So alpha is theta 1, beta is theta 2. So we input theta, and y minus alpha by beta, y square minus, so all this is coming from this equation, y minus alpha by beta, y square minus alpha naught plus 1 by beta square, 1 by t minus beta naught, 1 by t is 1 by y minus beta divided by alpha minus 1. So all of these, then we combine them in columns and then we just optimize them. So beautiful. Let's see how the program goes. So first t equals 10. We need to simulate the data, very default structure of simulating y when we don't have anything else. We haven't done a lot of y simulation before. This is probably the introduction to y simulation directly without the help of x or u. So now so round function is round, then random number generated with R norm got cold a bit, then RNDN, random number generated with R norm, and we have y, then we estimate alpha with only y. We don't have any other variables, we don't need any other variables. At 0 iteration when alpha naught is mean of y, g is numeric gradient estimated from our function, and our input was y. For alpha naught we are finding our numeric gradient. How we are doing it? Simply in MATLAB the function is num grad, in R the function is only grad. So grad alpha naught and y equals y. Then Hessian, numeric Hessian, and R it is Hessian. All this gradient and Hessian will not run if we don't install the numeric derivative package. So y equals y. So we have gradient and Hessian, concatenate and display starts always starts by n. and then it's comma, just like everything else is just like exactly like MATLAB. There's a little tweak in MATLAB. If you notice very well, whenever you are converting a number, a number to string representation, you do it inside a third bracket. But display function requires you to put a first bracket. Without a first bracket, nothing will work in MATLAB. Here, everything is in first bracket. No need for any other brackets, third bracket or so. So, objective function is the function's value, gradient, and Hessian. Then we go on. After the first iteration, we do update, Newton-Raphson update, where alpha 1 is alpha naught minus g by h. We represent this as vector, one vector, alpha naught we need x mod equals any, so as vector alpha naught minus inverse of h by g. So we, by any chance, we need to know that this is not gonna represent a matrix. Alpha 1 must be a vector, and it must be considered as a vector in the system. So in R, it is essential in such updates to mention this as a vector. So first iteration is simply gradient and Hessian calculation. Again we update alpha 2 in the second iteration as vector. Again we calculate gradient and Hessian, and then we go up to alpha 2. Then we estimate the variance of alpha, which is inverse of Hessian divided by t, and standard error is simply square root of inverse of Hessian divided by t. Another one solution is an iterative solution. In an iterative solution, we just optimize instead of doing the Newton-Raphson manually. So what did we do up until now? We simply estimated the numeric gradient, gradient or Hessian, numeric derivation. We did some numeric derivation without optimization. We can do an optimization now. In MATLAB is OptimSep large scale of display iteration, or you can put display as off. And we want alpha, we want the function's value, and we want Hessian. So at alpha, input alpha naught and ops initial value. Here the initial value optim will just do optimization alpha naught, then GMM crit initial value alpha naught. Do we have alpha naught anywhere before? Yeah, see, initial value is just the mean of the random value. Yeah, alpha naught, then the equation, and YY method is BFJS Hessian t, and alpha hat. After this optimization, the par value is updated with the estimated value, which is alpha hat, the estimated equation, then the Hessian, and variance of inverse of h by t gives you variance and square root. So this is simply with iterative. This is an iterative approach, which is the regular one we always do. In case of a third moment condition, we just call the grid 3 function, and that's all basically. Grid 3, In case of a two-parameter gamma distribution, we have two initial values 8 and 2. We just assume them. Okay, we just assume them, and with these initial values we just call. We're not sure that if in the question there is an initial hint on initial, there's no hint on initial, so we're just assuming 8 and 2. Doesn't really matter. Then we call the function, and yeah, the two parameter estimates are presented to us with a covariance matrix. This is already a covariance matrix, there is nothing new. So we put the whole thing except for the local functions, the whole estimation under a function, just like here, because it is easy to save. And remember, whenever we are creating a function, the name of the script must be equal to the name of the function, otherwise this program will not run. This was pretty simple code. Let's see what else we have to face. Estimating a student t distribution. Now again, everything else remains same. Our moments change slightly, tau minus 2, we're familiar with that. Now starting values, mean and tau. For tau is 5. Wow, so initial values are given in this case. In previous case, the initial value was given. Mean and tau, we estimate that, and just like before. So for second one, 3 nu, it's not tau, sorry, it's nu divided by nu minus 2, then 3 nu squared divided by nu minus 2, nu minus 4. We just need to remember that. And let's see, this problem is GMM student. So we do GMM student. Okay, in this problem again we create local functions, and it's exactly the duplicate of the previous problem. There is nothing new. In the local functions, first we do two moment conditions, but we are doing students t distribution. So mu is theta 1, nu is theta 2, because we have two moments. We don't only estimate mu, we also estimate nu. So m1 is y minus mu, m2 is y minus mu square minus nu divided by nu minus 2, that is m2 for us. Yeah, see, y minus mu square minus nu divided by nu minus 2. We combine them into moment conditions, and we have our optimization function that we have to minimize. Same thing. So column bind m1, m2, and then take column means, and the final one is again column bind the transpose one. Column means is important to remember that we do column means in the equation, column bind in the equation. Then three moment conditions. Well, you have mu, nu. So the up to this is okay. Then m3 y minus mu to the power 4 minus 3 nu squared divided by nu 2 minus nu minus 4. So this is the three moment condition. 3 nu squared y minus nu to the power 4 minus 3 nu squared divided by nu minus 2 to the power multiplied to nu minus 4. So we combine them again with column bind. We want them in columns. Then this is column bind again. So we specified our moment conditions, and then we move on with t equals 10. First we set our random seeding, then we either generate data or read data as matrix. Instead, I would prefer that we randomly generate data. It is good to follow one fashion. If we are to read a table, it's good to use as matrix function to read my table, so that the because here I want my table to be presented in matrix without any title. So zero iteration with where mean the initial values are given to us. Mean is y mean and tau is 5. With that we optimize gradient and Hessian, where we optimize gradient. We represent, because we are looking into transpose of that, so we do column bind. See, when we are doing matrix, a whole matrix to be transposed, probably we use column bind instead of T. Okay, here is a lot of huge use of column bind. Okay, the reason behind is that the transposition, we are transposing two columns all together instead of one vector. So two columns are being transposed, so we use column bind. Hessian is this. It is the same case as here, where the means we are having in two columns. Generally we use transpose when we have one column. Because we have two columns, we are doing transpose by using column bind technique. Okay, so remember, this is a very, very important thing to remember if you are using R. Okay, so up until this is fine. We print H to see what H has to offer. View and print gives you two different results. It's important to know about print function too, which gives a summarized result. Okay, then updating. Well, where I'm updating theta1, I need to, just like before, mention this as a vector. Theta1 must be represented as a vector. And if you don't, while you are including maybe suppose a variance decomposition matrix, and you don't need the title, if you don't convert that table as a matrix, then you might have error while you are running the functions. So it's good to know which one is a vector and which one is a matrix, and specify that in your programming. Okay, so Hessian, then this is first iteration, and with that technique we are updating theta1, and we are doing second iteration again with T is being, we could do is that use column bind. So they are showing you two techniques. You can also use transpose instead of column bind technique, but if you use column bind technique, that will do too. So, but always remember to follow one technique instead of using multiple techniques. This is for learning here, so we are going through multiple techniques. Then inverse of Hessian divided by T. Now in iteration, when we are doing optimization, we start with mean, then Y method is PFGS and Hessian, then estimate results, value, Hessian, blah blah blah. We did these displays or concatenate and display before, so you just optimize. There's no tweak in there. With optimization, optim set classical of displayer, then theta GMM create theta y not ops, where optim is theta not var value, which is var value, then the function GMM create 2, and y equals y. Method is Newton-Raphson, Hessian, and the results are. Then when you use 3 moment condition, then we use GMM create 3. So that's all. There is no other tweak in the whole program. It's that easy basically. So Hessian is true. If you make Hessian true, then it will automatically find Hessian. In MATLAB, on the other hand, you don't need to define anything true or false. You just have to activate the functions that you want to results that you want to display. That's all. So GMM student and GMM gamma is quite the same. With student distribution, this is the same as before, just the question is changing. Now the consumption capital asset pricing model, which we slightly hinted in our notes, and which was example 10.6. so we'll go up now. Before estimation, see, this was consumption capital asset pricing model, which is based on the assumption that a representative agent maximizes the intertemporal utility function subject to a budget constraint. No? Consumption capital asset pricing model, that is based on the assumption that a representative agent maximizes the utility function that is subject to a budget constraint, where consumption is real consumption and sorry, I'm just gonna see. Okay, real consumption, and E represents expectations conditional on all relevant variables available at time t. The parameters are the discount rate, beta, and the relative risk aversion parameter, tau naught. The first order condition is, this is the first order condition, right? With Ct plus 1 by Ct minus gamma naught. Well, taking first derivative here with respect to budget constraint, the first order condition is this equals 0. Alt is the interest rate and has the form of this equation, letting omega is equal to 1 plus et. We know the relevant where et represents real returns on equities. L is an exactly identified model of the form this 1013, and in 1013 what the form we had in 1013 was, the equation generally is followed by the omega or an exogenous variable, right? Because this is the condition, and this is conditional expectation, this is conditioning. So omega, the equation is conditional upon omega. Here the equation is conditional upon et. Yeah, omega is also here. So equation is generally followed by omega or et. That will satisfy for an exactly identified system empirical moment condition, which equals 0. And we expand the system to this. So this is what we are gonna do. Let's see what the question has to offer us. The data are 238 observations on real United States consumption ratio, Ct plus 1 by Ct, Ct plus 1 by Ct, the budget constraint, Ct plus 1 by Ct. Then the question, rest of the part is treasury bill rate RT plus 1 and the real value weighted return ET plus 1. This is the adjusted Hansen and Singleton dataset used in the original paper. Consider the first order condition of CCAPM, consumption based capital asset pricing model, where 1 plus RT minus 1 divided by multiplied to beta naught Ct plus 1 by Ct to the power minus omega gamma naught. Okay, now this problem is GMM CCAPM, consumption capital asset pricing model, and yeah, consumption capital asset pricing model is represented with here. Okay, let's see how the problem goes. We have data set, first order condition, it looks like this. we already are familiar with that, where C is the real consumption, R is the interest rate, discount factor beta, relative risk aversion coefficient gamma, estimate parameters beta gamma by GMM using omega 1, and instead of U use CT minus 1. Obviously before the function this will come, that's all. Starting values are given to us. Repeat using, now instead of omega we just keep updating the omega with R, with RT, ET as instruments, with RT, ET minus 1 as instruments. So this is conditioning for conditioning. That's all. That is the only tweaking part here. There is nothing else. So let's see. We'll obviously have multiple functions. First function, okay, first to, there is no simulation here, so we don't do set seed. First function, we have B C ratio R ZT, which is B C ratio R ZT. Basically we are starting with ZT is ET and ET minus 1, I guess. So we are starting with the last one. So size of ZT, number of rows is number of rows of ZT, number of columns is number of columns of ZT. ET is the residual. We're starting with that. So we identify this as ET. We start with that, number of rows and columns. Beta is B1, gamma is B2. Parameters are being estimated too. So beta, gamma, all of them we are estimating. C ratio we are estimating, and RT and ET all we are estimating here. So UT is beta C ratio to the power gamma multiplied to 1 plus R minus 1. Okay, so which calls for the equation from here, beta C ratio to the power minus gamma 1 plus R minus 1. So beta C ratio to the power minus gamma 1 plus R minus 1 UT. So K equals 1, M is zeros, length of M is number of zero arrays. Well, C will be rows and columns, number of rows and number of columns. Number of rows and number of columns, where is the T? Z is basically not E. Z is well, combination of all, I guess. Z has the elements of this is omega. Z is omega. So we start with 1. So it's an exogenous variable. We start with 1, then C ratio, then R, then E. All are taken in. So Z is important here. Length of rows, number of columns is all there. Number of zero arrays will be created for C number of rows and columns. So here 2 is column, 1 is row. So for J equals 1 to number of columns, just by that, number of columns, not number of rows. K is 1, M equals Z UT. M equals Z all rows K columns, which is just all rows. First one column, Z2 all rows J columns into UT. all rows j columns into ut z ut. Okay, so by zt I'm meaning all the combined. This is the combined of these, and ut is the residual. So we are talking about ZTUT because we are talking about the equation where the residual and all other elements are not correlated to each other. That is the point. So basically, where am I getting this ZTUT from? Okay. Here we have the function ZTUT, right? We have MUT function ZTUT applies to any subset of variables contained in omega t. Any subset of variables. This is the exact same thing that is we are doing with the loop, where MT is the function, right? Population function with we want the results to be one column for all rows, and when j is equal to 1 to number of columns z2, take all the rows up to j columns, multiply to ut, and k is k plus 1, which will automatically iterate. So this is the same thing. First, 0 arrays for c rows and number of rows and number of columns. We create a matrix of rows and columns for c here, right? Oh no, not for c, sorry, empty, for empty rows and columns for j in sequence of columns, all the columns, empty for all function for all the rows up to k columns. We have all the rows up to j columns and ut, all the subsets of omega t ut, which is updated, and it returns empty, this function. So define the moment equation, define the mean of the moment equation. So RZT whole thing, the mean is represented with RET. Also compute the optimal W function Q with Q. I'll call the optimal function B ratio Q RZT L max. D is MUK and B ratio R ZT MUK again is the moment condition. D have all the elements estimated here. G is mean of D. W is the weight matrix D transpose D. Tau is 1, well tau up until tau is less than the maximum number of estimation. Tau is D. Tau plus 1 size of D1. D tau plus 1 size of D1. Let me find equation for this. So the whole omega tau thing should come from here, as we know omega tau D inverse J, D inverse transpose, and we are familiar with this equation. We have discussed this equation before. Well, omega tau is this equation, right? Or we can also use this equation. So anyway, in either any combination is used, this is what is left for us. Transpose of D, G is the mean of D, then D transpose D that we have used. We are familiar with that. Omega is D transpose D. Tau, now omega tau is size D1, I mean tau plus 1 to size D1 transpose for all rows, then 1 to size D1 minus tau. So this is kind of like a lag system. Tau plus 1 to size D1, then size D1 and minus tau, so the dimensions match. Omega is omega plus 1 minus tau by L max multiplied to omega tau transpose. So this is something optimal for optimal omega. This is something being estimated for optimal omega. Okay, and just for now, just remember that, and let's move into I'm not sure if in actual equation there is something with tau given. Not much. Okay, we'll see if there is any more use of these. We'll try to get into that later. So then we bring in our data, then ZT. Now here we have ZT, we also have E, right? Now we have ZT, which is kind of like an exogenous variable. We're starting with ones, so replicate T, or replicate 1 T times, then we take the lags actually, because C ratio 0 1, trim R 0 1, trim R E 0 1, so we all trim the function. This is initialization, then we do in search for the parameters, we run the optimization. For C ratio, we store our results, and then we do gradient, and then we find optimal tau, running the function. Again the loop comes in that we just discussed, while it'll go on up until convergence as long as tau is less than L max. This will have these functions, two functions will continue. Hansen J test. Okay, basically there is quite a lot of gray area in consumption based capitalistic pricing model, because it's an economic based theory, and I'm not sure that we are using any of the discussed theories. That's why we are a bit lost here. Let me try it one more time. What I'm looking at is tau plus 1 going up until size of D for just taking one column, size of D rows for one column. So we are accessing D, and we are taking tau plus 1 first, starting from tau plus 1 to size for all the columns, then accessing D again. We're starting from all from 1 to up until now, this time to match the dimension minus tau, size D1 to minus tau, because here we skipped 1, so we remove 1 for all rows, and then omega is 1 minus tau by L max plus 1 W tau. I'm not sure what this equation is coming from, so just remember that. So let's move on to the next problem. Instead of hovering around here, decomposing international equity returns, or GMM equity. GMM equity, we have here GMM equity. Okay, this time the problem at hand is quite interesting, very much similar to my research area. Here you're gonna decompose international equity returns. We have data file containing equity prices, S&P 500, FTSE 100 index, European 50 from 2004 to 2009. we have a residual, which is RIT minus mean return minus mean return. Actual return minus mean return represents centered daily percentage. Equal return, equity returns is log of price difference multiplied to 100, which is daily percentage equity returns. Now we want to compute the covariance matrix of EIT first and interpret its moments. So for the covariance matrix, we know that to find that we have to optimize first. Consider the latent factor model. Latent factor model EIT calls C gamma IST plus phi IZIT. So here EIT is the latent factor model, and this is called latent factor model because we have the latent gamma I, which is the indirect estimation, where ST, Z8, Z, Z1, Z2, Z3, the IID with 0 mean, 1 variance. The theoretical moments are gamma I square, phi I squared, and gamma I, gamma j is the variance. I is not equals j. There will be loops in this, as I can see. So S here is not gonna be is not directly located anywhere. So, but well, in the process of estimating E with the help of Z, which is the combination of all the elements, we basically retrieve S and gamma, which is S is the latent, the factor loading gamma I. Well, this one is the factor loading, S is the latent factor, and gamma I is the factor loading. Using the moment structure in part B, estimate the parameters, the factor loadings, and all the coefficients by GMM. Interpret the parameter estimates by computing the relative contribution of the common factor with idiosyncratic factors given by, so that the factor decomposition gives an exact decomposition of empirical covariance matrix computed in A. Okay, sure. Let's see how this goes. Quite nice, right? So first we need to look into our problem. Do we have any local function? There's one local function. So we are creating a function GMcrete with the parameters and the residual with lambda. There are 3 lambdas and 3 phi's, right? Sorry, this was lambda, was calling it the gamma, I'm sorry. So 3 lambdas and 3 phi's. A, on the other hand, is the lambdas and the diagonal elements of the phi's is A. So combined lambda and the diagonal phi's, which should give me A, right? Okay. A means BSX1. BSX1 is a function that we use when we are doing anything on to multiple matrices, right? Instead of BSX1 in well, we can mention in our R function if that is a matrix or a vector. So matrix, creating a matrix where we are minusing from E2 vec A transpose is being well removed. So vec is a function. Let me explain you what vec is. Vec is a customized function that we are using in R and MATLAB both altogether simultaneously. What vec does is that vec stocks columns of X on and below a diagonal. Okay, so if you have a diagonal matrix, you stack the column of x, you stack the columns of x on the diagonal and below the diagonal. Okay, so the diagonal fits inside the matrix. So rows and columns, number of rows and number of columns according to size of x. For I is equal to 1 to number of rows, y xi equals 1 to I. So columns of y is equal to y transpose. So it stacks on and below, that stack columns of x on and below the diagonal. That is the vec function. And as we know now, we are gonna see how that has been used in our local function. So in our local function, we stock them together, vec A and A transpose, because A has two elements. One is lambda, and first 1 2 3 lambda will be in columns, then diagonal of phi. Okay, so diagonal of phi is phi will be in presented diagonally 1 2 3. So you see, dimension is a kind of like a problem. So when we do vec, we make it a matrix in cases similar to this. Okay, so because we don't need all the phi's, we just need the diagonal element of the phi's, because we will have a lot of phi's given our number of parameters to estimate. We have a lot of parameters to estimate. We won't have a lot of factor loadings, but we will have a lot of phi's, and we might have a square matrix with phi. So we just need the diagonal elements to combine with our latent factor, so that they match. So we are creating a matrix vec A transpose, and we are removing residual from that matrix, on that is our M. So M is a matrix. First we represent our residual as a vector, then we represent everything else as vector 2. So this one vector minus as vector is vec A transpose. So the simple minus transpose, where number of rows is number of according to E2, number of columns is according to E2, by row is T. And then we have our weighting matrix MM transpose divided by T, MM transpose divided by T, and then we have our Q, which is half mean of M transpose. So column means M, inverse of omega, then C bind column means M, and we return Q. And then we move into, with this unconstrained objective function, we move into our main equation, main coding. First we start with clearing the screen, then we load the data, read table, equity decomposition. So if we read the table, that compute centered equity returns. So just now we are doing housekeeping. Equity returns, C log PT minus 1, then ET is base x1, residual is RT minus 1, which is simply coming from here, RT minus mean, see, mean of RT, RT minus mean of RT, column means. T is equal to length of ET. Generates C squares and cross products of columns of ET. I told you that we'll have some loops coming, right? So rows and columns is size of ET. Rows, we have to separately define rows and columns. E2 is zeros, so replicate 0, not replicate, array of zeros, and the function matrix is rows and columns into columns. So column squared, rows, number of rows, and columns squared. because we are generating squares and cross products. So k equals 1, j equals 1 to number of columns, I equals 1 to number of columns. So by row and by column will have elements that is equal to the dimension of the number of columns, because in columns are stocked all our parameters. So E2 all rows up to number of k, all rows one column. E2 is just one column. In one column I want ET multiplied to ET squares, right? ET is all rows j and all rows I, basically same size. I'm just squaring ET and I'm adding k plus 1 every time, right? K equals k plus 1. That's all. Column ET plus 1. So generate squares and cross products of columns. ET very important. I'm giving you 2 minutes to have a look into it again. I'm creating a matrix of ET by generating squares and cross products. Squares and cross products are essential in GMM because in theory also we see that we have had a lot of struggle trying to understand the cross products and in GMM. Now we're gonna drop repeated columns is all rows, and then we vec reshaping. So reshape is simply reshaping. Still we can, reshape according to Gauss is reshaping. One rows till number of columns squared by 1 columns. We can still have a look into what the reshape function has to offer us. So the reshape function reshape a matrix to agree with Gauss reshape command. We have y number of rows and columns, right? So we have y, which is 1 to number of columns squared, number of rows and number of columns. So we drop repeated columns with this code here. This is kind of something to remember as well. All rows, then we do vec stocking together, and we are reshaping this. So two things: we generated cross product and we dropped repeated column. Step 1 is to generate cross product. Step 2 is to drop repeated column. Okay, so cross products are generated by making squares of columns, then repeated columns are dropped from these squares, then we estimate with our regular optimization. And in theta we estimate theta parameter and standard error. Then J statistics is new, the size E2 minus length of theta. How do we estimate J statistics? J statistics is estimated through we need to have a look into this. So we have J so this is new to TQ. This is new. If new is greater than 0, we find this percentage value. That's all. Cool. covariance matrix based on decomposition. The residual is now represented as a matrix. Covariance matrix A transpose is a covariance matrix. Covariance matrix of data is A transpose divided by T. Nu is 2 TQ, or the nu is simply size E2 size, right? MATLAB size is here. Where is the size function? Nu. Let's see how nu is size, right? We're still waiting for size. So important thing to remember, whenever you're using size function, second, if we mention 1, we don't generally mention 1, or if we do mention 1, then the function captures how many elements are there in your rows. If you mention 2, the function captures how many elements are there in your columns, right? There is one more thing I need to show you actually before moving on. Just popped into my mind. Okay, we'll skip it, we'll talk about it later. So very important is square and cross products, and then dropping repeated columns. Then we came up to here, common idiosyncrasies, and basically theta squared, I mean all of the elements are being squared, and so the lambda squared divided by total gamma squared. So this is coming from the question actually. So you see sigma squared, phi squared, elements are being squared. Then theoretical moments of EIT are, and this is the second moment, this is the first moment, this is the second moment. So second moment is they're being squared, I and j, square divided by sigma square plus phi square. So sigma square, phi square divided by total, then this is divided by total. That's all, very simple. Total is simply this, yeah, this is divided by total, this is divided by total. Total is simply this. Before that we had a covariance matrix based on decomposition is A transpose. We are familiar with this representation, so here it is important to remember that this representation as well. So size of E22 is number of columns you have, nu is number of columns you have, I think it's the degrees of freedom here to take you, okay, minus length of the parameters, number of columns in residual minus the length of parameters. If that is greater than 0, if there is more parameters in residual than the total number of parameters, then we check for chi-square, we check for statistics value. Just statistics is simply 2 into t, 2t in q, 2qt or 2tq. Okay, fine, that's fine with me. Simply that is that mentioned in the question, 2tq. Okay, just remember that. So there's the value of the objective function 2tq. If there is more parameters in residual than the number of parameters estimated, theta, then see the significance of, check for the significance of the J statistics or OPG. J statistics is generally needed as OPG for OPG. And then covariance matrix based on decomposition, fine. Then common idiosyncratic is coming from, common idiosyncratics are this, vectors are being estimated from here. Okay, so that is GMM equity. Next problem is, so what important things we learned in GMM equity is that first of all we take residual dimension is very important. Looking into residual dimension, we decide whenever we are talking about equity returns, basically we decide we take lambdas and phi's. Lambdas are stocked in columns, phi's come in the autoregressive parameter. Phi's are autoregressive parameters, so phi's don't only come in columns but they are coming in matrices. And we're familiar with this nonlinear model criteria calculation because let me just show you where we have dealt with autoregressive parameters before. Okay, before moving any further, we are getting confused in some steps, so we have decided to look back. You see, we are deciding 2 sigma square, 2 alpha naught is the second moment. So whenever we are estimating 2tq, this is coming from this concept. Okay, one very important thing is J distribution. Now J is coming from variance. MT alpha naught is the J is the variance of our moment condition, which is a combination of squares and cross products. Okay, so that's why we need to estimate squares and cross products. And tau, on the other hand, is representing m transpose at a different point in time. So you see, in the previous problem when we were discussing WT, we were trying to measure WT. What was the previous problem? Let me go back to the previous problem. WT, yeah, consumption of capital asset pricing model. Let us just open the file. Consumption of capital asset pricing model in the discussion GMM. GMM says CAPM, right? There you go. Okay. Come on. Let's just, the computer has gone a bit slow, so I'm just gonna pause here and wait for that to come up. So you see, when we were dealing with tau here, obviously when we were talking about J has products and cross products. J has products and cross products, right? Products and cross products. Hence, we had to take multiple columns when we were estimating M, the variance of M, which is J, right? And there was more where we got stuck, which is omega W. The W was d transpose, as we understand, was quite simple. But what about tau? We had tau, when we were estimating tau, we had W tau, which was d tau plus 1 size d, then size d minus tau, because the reason is simply this equation. You see tau m theta, then mt minus I theta. So tau is changing. First is mt theta, then mt minus I theta. Why? This part is increasing, the theta part, mt theta part, which is tau plus 1 to size of d, number of rows actually, the number of rows you have in d, up to that has been transposed indeed, because it's kind of like decomposition, multiplied to 1 to size of d1 minus tau. So each time you add 1 you reduce from behind, so it's just a lag function, mt minus I. Then W equals W1 minus tau divided by L max plus 1 W tau transpose. How we are getting this function? See, we're starting with, here we're talking about tau, W plus 1 minus tau, right? 1 minus tau L max. What you can do, you can just simply take tau on the left hand side, everything else on the right hand side. So you have W plus W1 minus W1 minus tau. See, things inside are changing because of these things inside. This equation is expressed as this: 1 minus tau divided by L max plus 1 W tau transpose. So 1 minus tau L max plus 1 1 minus tau L max plus 1 is this: 1 minus tau divided by L max. Basically you take it on the left hand side, and W tau is represented with, isn't it? I mean, let me just, no, I'm sorry. W equals W, fine. Then here this one is 1 minus tau L max minus 1, then W tau and W tau, W tau and W tau, or the whole thing is W tau and W tau. So this is coming from here, that I understand. And W here, this part is the confusing part. W is there because W plus 1 minus tau divided by L max plus 1. So the whole thing is W minus plus 1 minus tau divided by L minus 1. If you just remember that, that will be much easier to remember. So this caused these functions, right? Now we are in GMM equity, and what we are talking about here now is, as we have seen how GMM equity works, now we can move on to one more stuff, is that there is nothing more. So efficient GMM estimator, fine. Now let's move on to the next problem, GMM contagion, which will be similar to GMM equity, because here also we need to find products and cross products. Then we have to drop repeated columns, right? That is the only tweak here. That is the only thing that we need to kind of memorize or remember. So let's see if there is any function. First, let's read the question. Modeling contagion in Asian crisis. The data file contains daily data on exchange rate of the following 7 countries: South Korea, Indonesia, Malaysia, Japan, Australia, New Zealand, Thailand. The sample period is from 1997 to 1998. 319 observations. Let the residual be this, represent a zero mean daily percentage currency returns be this zero mean daily percentage currency returns her SIT. Okay, SIT minus 1, SIST is our latent factor, gamma I is our sorry, I keep making the mistake. This is, yeah, gamma I, you're right. Gamma I is our factor loading. So we have 7 countries. So there, this one is lambda I, and this is gamma 70, where the factors are all 0 mean 1 variance. For each country, estimate proportion of volatility arising from contagion by, so how we take the total parameters and we divide that, we take the ratio, that's all, of each parameter to total for each country. So perform a test of contagion. So now we do a hypothesis testing where the gammas are 0 or not, right? Because gamma 7 is 0, but the factors are all ideal, 0 mean 1 variance, gamma 7. So let's see how this works with contagion. So first unconstrained and then constrained. Okay, so in case of unconstrained function, we create the function GMM create with theta including all the parameters. Theta will have all the parameters, unknown parameters, and we have residual. So lambda is the first 7, because 7 countries, we have 7 lambda and 7 kind of like autoregressive parameter phi. Then we have gammas. How many gammas? We have 5 gammas. The question is, why do we have 5 gammas? So start with lambda and then gamma. Gamma 7 equals 0. To gamma 6. So unconstrained. Okay, fine. We take 5 gammas here because the last gamma is 0, right? With the last gamma being 0, okay. We do that here too. Function GMM create VE2 lambda. We take the 5 gammas and column bind A. We are creating the product cross product variance covariance matrix. Lambda and diagonal of phi, column bind lambda and diagonal of phi values. Just the diagonal of the phi elements. Diagonally, we are representing the phi elements diagonally. Then 1 to 6 rows. From in 1 we have 1 to 6 rows in the 8th column. Here we have 7 lambda, 1 2 3 4 5 6 7. Then 1 1 2 3 4, yeah, the last one, right? Then you have 7 columns here, 1 2 3 4 5 6 7, because they're diagonally. So we have 8 actual columns here, and the 1 to 6 elements in the 8th column is represented as being gamma. Fine. the last, we're looking into the last column, and we're taking the seventh gamma is 0, so we are taking 1 to 6, and we are representing that as gamma. Currently there is none. Okay, currently there is none, but gamma will be stored there. So the matrix looks like this, means this like a Z. So BSX1 is, we stock them together and create a matrix A transpose. We minus that from E2, so T is equal to, instead of BSX1 we can try apply, without that we can do 2 if we just put matrix, you know. This is another way to do it. Apply E2 1 minus transpose of back. It's not necessary, we could have done the way we did with the previous problem, just taking matrix inside the bracket. You just put everything as vector, so E2 as vector minus as vector this whole thing, that's all. Then omega is we know that, and the function is also known to us, column means, and last one is column bind, column means. Fine, return Q. Then the constraint. Now in the constraint one, everything else up to 5 is fine. Gamma is zeros, we don't have any gamma here. Everything estimated together, 15 to 20 will be our gamma values. 1 to 6 where the gamma will be stored. Here zeros, 6 rows and 1 column. The seventh is not being estimated, 6 rows and 1 column. So lambda diagonal of gamma, again gamma's place is where it is. Again we do everything as before. Then we're gonna model the contagion. How we're gonna model the contagion? We're gonna do simulation here as matrix, and we just simply regular way we do the find the tremor in the regular way, which is RT minus RT minus mean minus RT. We could just do matrix as vector thing. See, it will be looking like this: matrix as vector, RT minus as vector, column means RT. That's all, very simple. Then you have residual of RT, all rows, columns, 1 2 4 7 5 6 3, 1 2 4 7 5 6, because we want our residuals to store lambda 5 5 5. Oh no, 7 1 2 3 4 5 6 7 7 5 6 3. Okay, the way I want. I'm just playing with the residuals, you know, appearance, order, nothing else. Then we do just like before, squares and cross products. Rows and columns will come from the size of ET. Then E squared is zeros, because we're going to square the residual number of rows and columns to column squared for cross products. So K equals 1, that will continue to update. J is equal to 1 to columns for J in sequence columns, then for I in sequence columns. Then all rows, K equals 1, that will update KK plus 1 for 1. All rows 1 column, it will be all rows J multiply TT, all rows I, all rows J, all rows I, there will be squared. See, J's and I's squared, KK plus 1, it will end, and drop repeated columns, right? So we took all rows, then we do vec, stocking together, reshape egg, 1 to 1 columns, sequence of columns multiplied to columns, multi-columns, sequence of multi-columns, multiplied columns, y, rows, columns. Reshape egg has three nodes, y, rows, and columns. So y, 1, 2 columns, multiplied columns, sequence of columns, multiplied columns, rows and columns. Then unconstrained model is being estimated with theta naught is random, 20 rows, 1 columns, or running optimum E2 is equal to E2, method BFGS. J statistics is 2Q to TQ. New is in column minus length of the, so number of column of the residual minus length of theta. If that is more than 0, we do chi-square, just like before. Nothing else is changing. So total is being added together, and then the idiosyncratics, common idiosyncrasies, or the contagion is simply this one divided by total gives us contagion measures. Parameters squared divided by total parameters give us the contagion measures. And in case of a constraint model, we do the same thing. 2t statistics is 2t qc minus qu, qc minus qu, that's all. 2tq, it had 2tq, now it's 2c qc minus qu. Nu is the degrees of freedom, so we are measuring the degrees of freedom here, that's all. So measuring contagion is pretty easy, especially contagion and equity is both has a very common thing to do, which is cross products and dropping repeated columns, that's all. So GMM contagion covered for us. Now we just discussed two very important application of GMM. We will talk about another problem, GMM consistency. Now in this problem we simulate 100,000 observations from the gamma distribution, where the initial parameters are given to us. We need to compute GMM population objective function using this weight matrix and M. We know weight matrix is alpha 1 by y, 1 by alpha minus 1. This is familiar to us. Basically this consistency problem is also discussed earlier. Let me show you. Here in our notes we talked about consistency and GMM with gamma distribution, where we had two population moments, empirical moments and population moments, where Q was there, blah blah blah. So we did this. We are familiar with this. In fact, if we move forward, we see the exact calculation defined here, where we have 3 population moments and 3 weight matrices, right? So this is exactly what here talking about here in this problem. This is the same thing. Okay, and then we go back, right? We remove one more population moment and we try just one population moment. So function is alpha y, y minus alpha, y square minus alpha, alpha plus 1, 1 by y. So d1, d2, d3, very simple, right? Coming from those 3 uncentered moments. Then we take mean with omega, and q is simply g inverse of omega g transpose. G inverse of omega combined g, instead of g transpose we took combined g, return q. Then we just demonstrate population t is equal to 100. We are gonna do 100,000 estimation. We do randomization. Alpha naught is given to us, right? We have the initial values to us, which are we initialize with alpha naught 10, beta naught 1. So alpha naught 10, alpha is 6 to 14, increasing 0.1, This is something we are just assuming. Gamma random distribution. So interesting, not only random distribution but gamma random distribution is another simulation with gamma random. It's not normal distribution, it's not uniform distribution, is gamma distribution. So R gamma or gamma random distribution, which is taking initial value alpha naught, 1 row, t rows, 1 column. Okay, so 1 to t. Oh no, alpha naught 1 is the shape, t rows, 1 column. Shape is 1. Okay, alpha naught is the initial value, shape is 1. So t rows, shape is alpha naught, rate is 1. So sorry, shape is alpha naught, rate is 1. So shape is alpha naught, rate is 1, t rows, here t rows, 1 column. That's all. And zeros, length of alpha 1, replicate 0 for, or we can do it with array 0. If there was column, we could have just given column, but zeros can be represented with replication also. Replicate 0, length of alpha is equal to 1 to length of alpha. We do okay because we have t is equal to 100,000 for, so length of alpha is 6 to 14. T is equal to 1 to length of alpha. We do this estimation, we run the equation for 6 to 14. Okay, by 0.1. So 6 to 14 by 0.1 is quite big, right? So finite sample distribution is when zeros length of alpha and 4 columns, t is equal to 50, k is equal to length of alpha, tmp y 1 to t, alpha k rows, t columns. Finite sample distributions. And then that is just well, just to show that this is just to show that as number of samples increases, this becomes asymptotic. That's all. K rows, 1 column, in 1 column up to k rows, right? K is 1 to length of alpha. Alpha is, well, just to show asymptotic property, t is equal to 100. We keep on updating. In the second column we have 1 to length of alpha when tmp is 1, y is equal to 1 to t, tmp rows, k rows, tmp columns, alpha k rows, tmp columns. No, not column row, what I'm talking about. Alpha and y, alpha distribution, tmp, y size will be 100, y size will be 200, y size will be 400. Finite samples. And this was just population distribution, calling the function itself. That's all. No optimization or anything. That's all. And then we represent them with figure, and we show as number of observations increase, we see consistency. Okay, so population moment is also being achieved from our sample moments. That's all. 100,000 observations are achieved from 6 to 14. When you do 0.1, this changes in between them. 6.1, 6.2, 7.1, 7.2. So kind of like that. So we are not taking 100,000 anywhere, not at all, because that will be too much. Oh no, yeah, we are taking 100,000. 1 column. See, this is 100,000 distribution. Okay. All right. This one is for the rest 100 observations, so but 100,000 is being used here. So this was quite easy, no difficulty. The other problems, the next problems that we have are, besides we have Monte Carlo evidence for gamma. I'm not sure that I want to go into this Monte Carlo evidence. Monte Carlo evidence GMM, SIM. Let me see. Yeah, I really don't want to go into Monte Carlo evidence now. This is huge, and besides we need to complete the chapter on Monte Carlo simulation. Then we might be, if we're interested in simulation, we might come back. Level effects of United States interest rate, I'm not interested as well. Risk aversion and equity premium puzzle, again I'm not very much interested in this. I'm very much interested in contagion because that is what my focus is. I'm working on contagions, and so I don't want to confuse with anything else. However, if we are to look into the risk aversion problem, again the steps are very simple. You just represent, create the function, okay, there will be flags, that's all. So, and then load the data, adjust sample size, identify weighting matrix. If there is no flag, we want to run this optimization function with jstat. If optimal weighting matrix, if there is a flag, then you run, the difference is theta q theta c rbrs, no difference, theta 2t q min, flag 1 and flag 0. Results using identity weighting matrix, results using optimal weighting matrix. So just two different optimization will come in, that's all. If flag, we identity weighting matrix, if optimal weighting matrix, if flag, we do identity weighting matrix, so all one. That is the only thing in risk aversion, because this is relevant to our question, where the question suggests, well, consider instruments 1, identity and optimal. GMM with instruments, identity and optimal, that's all. Identity and optimal weighting matrix. So that's all, nothing else. Identity and optimal, with that you run to for risk aversion. This is all just adjustments, housekeeping, instrument, analyzing instrument. Instrumental variable is analyzed with constant, and RC is the consumption. So constant and the stream consumption. So the sole constant is once, length of RS minus 1. So this is once, and this version, that's all. Adjust sample size. Now we are just checking that the dimension matches. I say 0 1 because we are doing 0 1, this is 1 0, so the dimension will match. As the dimension matches, then we run the function, that's all. Times, this is coming from M1, M2 and M, these are all C minus gamma, and instrument, so these are coming from this equation. 1 minus 1, see, so times this one times this, minus 1, the whole thing, minus 1, multiplied to number of instruments. This whole thing is multiplied to instruments. and our instrument is lags. When we are taking lags, that's what we are supposed to do. It's a time series returns of equity bonds and consumption, and these are the first order conditions. So repeat B with instruments. So instruments is, this is another principle we need to remember. Real dividend, real stock price, returns are taken. Instruments is ones, -1, length over s -1, dimension 1 column, then C01, and then adjust the size. That's all. So very simple, you see. And I'm gonna avoid the other two problems. I don't think they're very important. And here I bring an end to the applications. Thank you.